Thank you very much, Daryl. Welcome everyone to the next in our seminar series, as Daryl said. So today the focus for our seminar is talking about our Raman microscope. And really the thing that I want to try to instill for people with this webinar is to think beyond just spectroscopy, beyond just the spectra that we can obtain with this particular instrument, and think about some more interesting experiments perhaps that you might be able to achieve with all of the expanded capabilities that our instrument offers you. So as is fairly standard with these seminars, I'd just like to highlight the platform and the broad capabilities that we actually have within MCFP. So we cover kind of 6 main node areas of research or capability on our platform, from mass and flow cytometry through X-ray characterization, fluorescence imaging, AFM, electron and ion microscopy, and nanofabrication as well down at MCN. We are part of ANT Victoria as well, so we're the UOM hub for ANT Victoria. You can see the team here on the screen as well. So please do reach out to us. We are all very, very friendly people if you have any questions about anything. And you can visit our website, of course, at any time to see all of the capabilities that we offer and to stay in contact and in touch with the different events that we are putting on throughout the year. And you can visit our LinkedIn page and our YouTube page as well, just to see the other content and stuff that we share publicly. So, basically, we want to start off talking about Raman spectroscopy and what it is and what it can tell you. So an introduction into the instrument itself. So Raman spectroscopy, it is a non-invasive, non-destructive, label-free method of probing the physical and the chemical makeup of materials. And because of this, it has very, very broad applications. So if we take this slide directly from Renishaw, we can see the very broad application space that particularly the inVia Raman microscope that we have in MCFP gives you, but also Raman spectroscopy in general. And it covers a majority of what we do in chemical engineering, of course, but then also into the physical and the chemical sciences, and indeed the life sciences as well. So very, very broadly applicable technique. And we're trying to expand that with our instrument in particular, and always making this instrument available to researchers to try different things. And that's really part of what I wanted to do today with this particular webinar, is to highlight some of the interesting things that our users are doing with our instrument. So let's just go back to the basics and start to talk about the Raman spectroscopy technique and what we're actually doing here. So the first question that we want to discuss is, how does light actually interact with matter? So we really have 4 main ways that light can interact with matter. Light can reflect from a material, it can transmit through a material, it can be absorbed by a material, and then it can scatter from a material as well. And with Raman spectroscopy, we are really focusing on the scattering part of this diagram here. So we're looking at the light that is interacted with the material in some way, and it has scattered from that material. And as a result, it has changed in some way through the excitation of different mechanisms within that material. And the main way that light will scatter from a material is either elastically or inelastically. And by elastically, we mean basically that the light will go in, and then it will scatter from that, and then it will come out, and it's unchanged effectively. So this part of the diagram here is referring to that, and we call this Rayleigh scattering. So the light going in is basically the same as the light that's coming out. It's a very, very intense signal, of course, because we are using a laser to excite our samples. So effectively, we're looking at the laser bouncing off of your sample. Therefore, it is very, very intense signal. And then we have 2 forms of Raman scattering here, Stokes and anti-Stokes scattering. And these are very weak signals. So the Stokes scattering here, where the light loses some amount of energy by inducing a vibration in the material, this is a very weak signal. About 1 in 10 million photons will scatter in this particular way. The anti-Stokes Raman scattering is where the light that is emitted has gained some energy, is even weaker again compared to this particular Raman scattering. Now, most instruments, lab-based instruments, when we're just talking about Raman spectroscopy, really would be focusing on this particular scattering effect here, where you've lost some amount of energy to a particular molecular or crystal vibration. And that's what we're focusing on. That's what we're talking about today with our instrument. And it makes sense as well to compare Raman spectroscopy with infrared spectroscopy. And if we bring this into the context of MCFP and the two vibrational spectroscopy instruments that we have the Renishaw inVia Qontor Raman instrument, and then we have the Bruker Lumos FTIR instrument as well. So if we just compare and contrast these two methods, this can give you a bit of an understanding on which technique is probably going to be better for you in terms of vibrational spectroscopy. So as we've already said, Raman spectroscopy relies on the inelastic scattering of light, whereas typically FTIR will rely on the absorption, the transmission, or the reflectance of light. Raman depends on a change in the polarizability of a molecule, changes in bond lengths typically. FTIR depends on a change in the dipole moment of a molecule. So Raman is sensitive typically to homonuclear vibrations, or can be very sensitive to homonuclear molecular vibrations. And this is often applied to things like carbon-carbon bonds within particular lattices and nanomaterials. So we can see the difference between these carbon materials in Raman. With FTIR is typically sensitive to heteronuclear molecular group vibrations and polar bonds, such as OH groups, for example. A big benefit for Raman spectroscopy is that there can be little to no sample prep to obtain results from materials that are Raman active. And what this means is, because we are effectively just focusing a laser light onto a sample and looking at what scatters off of it, it is very simple to prepare samples, get them into the instrument, and get results. Whereas with FTIR, there needs to be some consideration between about the thickness, the uniformity, and the concentration of your results, of your sample, and this can affect the results. So you need to think a bit more carefully about how you are preparing samples to present to an FTIR microscope. In Raman, as many people will know, fluorescence is often an issue. Big broadband fluorescence will swamp the Raman signal because it is such a weak signal. With FTIR, that's generally not an issue. In each case, they both obtain a spectral fingerprint of a material, as in they will identify for you a material, an unknown material, when compared to a reference material, for example, and they are complementary to one another. And what that really means is, if you were to use both techniques, you are getting a very well-rounded understanding of what your material actually is and the chemistry that's happening. So they are complementary to one another. So if there is an opportunity to use both systems to try to characterize your sample, you are getting a very complete understanding of the molecular makeup of your materials. So let's now have a quick overview of the Raman instrument at the MCFP. So as I said, this is a Renishaw inVia Qontor Raman microscope. And this is quite a well-equipped instrument that we now have. We have multiple laser excitations. So we have 532 nanometer, 633 nanometer, and 785 nanometer excitations. And along with these, we have the different filters accordingly here. So we have a 100 wave number filter for the 532 and 50 wave numbers for the two newer lasers here, the 633 and the 785. And this is basically how low or how tight we can go to the Rayleigh edge and still see a Raman signal. We have 3 different gratings on our system, a 1200, 1800, and 2400 line per millimeter gratings. And these are mounted onto a motorized wheel. So we always have by standard, the 1200 and the 1800 gratings installed, which means that changing between laser wavelengths, and this includes the filters as well, is just a change in the software. There is no physical change of the optics in the system itself. Our lasers are point sources. However, we also have the cylindrical optics to allow us to convert all of our point sources to line sources. So we can do things like streamline mapping. We have 4 different objectives: a ×5, a ×20, a ×50 long working distance, and then a ×100 objective. The stage is a registered and encoded stage with 100 nanometer precision, which means that it is software controlled and software monitored as well. The entire instrument sits within a class 1 laser enclosure. So this is a class 1 laser instrument, meaning we don't need laser safety glasses when operating it. It is a very safe instrument to use. And then the entire system is sitting on a passive vibration isolation table as well. We have Lincoln heating and cooling cell for this instrument that is software controlled. And we have some fairly nice sample handling accessories here. So we can be very flexible in the way that we can work with a broad range of sample types. And then finally, being a Qontor version of the inVia Raman instrument, we have access to the stream mapping modes and also the LiveTrack focus tracking on this instrument. And also built into this Qontor module here is an internal silicon reference that we can always use for intensity referencing and X-axis calibration as well. Many might not have actually seen what this instrument looks like when it is operating. And back when we had the bushfires a few years ago, there was an opportunity for Derek of Warsash to actually take a photo inside the University of Sydney instrument. They had a lot of particulates in the air, so as a result, they could very clearly see the laser beam path. So this is a bit of a sneak peek inside what's actually happening with the instrument, just to get a bit of a feel for how this instrument operates. And basically we have from the back of the instrument, the lasers coming in from the laser arm, and this is the 532 green laser. It then hits beam steer mirror right, which directs the laser in towards the pinhole and the beam expander, and then onto beam steer mirror left. And for users of the instrument, this is the mirror that you are changing when you are aligning the laser spot to the center of the crosshair. The laser path then goes through the cylindrical optics if they are put into place here, and will bounce off of this part of the filter to go through the podule and down the objective turret, through the objective that you will have chosen, onto the sample here. And this is where your Raman scattering is going to occur. And then your scattered light comes back up through the objective, passes through the filter wheel here. And this filter wheel is the part that removes the Rayleigh scattered light, allowing only the Raman scattered light to pass into the spectrometer here. The grating is mounted just up inside of here, and this is where it actually creates the spectrum for the instrument, passing it then out through the side of the instrument to the detector, where the spectrum is ultimately actually detected and presented to you. Okay, so in the technique, what we are doing here is we are recording light intensity and then plotting that against energy. So we record the intensity of our laser light and present it against this particular x-axis here. And we call this, the units of this x-axis are in Raman shift or relative wave numbers. And the reason for this is this x-axis is presented relative to the excitation wavelength that you are doing. So it is a loss of energy from your incident laser light. And what you can see here are, so these are 2 examples of polyethylene, where there is a very small but subtle change in the crystallinity, basically, of this material, and it can be seen in the Raman spectrum with these arrows. So this is what we're collecting using the instrument. And what does this spectrum tell us, or what can this spectrum tell us? Well, generally, the position and the relative intensity of those shifts and those peaks will give you the fingerprint for that material. It will identify a polymer or a material, an inorganic or an organic material. And then internally, the fine structure within those peaks and those bands can reveal more interesting information about, for example, material stresses, variations in the crystallinity, and also, of course, the actual amount of relative materials within a sample as well. And then if you were to take those spectra and collect them from a large area with some kind of spatial information attached to them, you can then use that to reveal information about how homogeneous your sample actually might be. So if you have different domains, you can identify those different domains with a Raman microscope. A few examples here from the spectroscopy side of things really highlights the power of the technique to identify different phases of materials that are chemically very, very similar. So the top two, for example, we have silicon carbide and titanium dioxide, chemically very, very similar to the point of being identical. However, the different crystal structures that these can be arranged in will give different Raman spectra. So this is the silicon carbide, different crystal arrangements here. And this is the rutile and anatase forms of titanium dioxide. And you can see that the spectra are distinctly different. And similarly, we have diamond and polystyrene, effectively carbon. Obviously, polystyrene, the chemistry is quite a bit different, but the spectrum is accordingly very, very different as well. So it is excellent at identifying materials that have similar chemistries, but very different crystals and phases. So then this now brings us to the next part of the talk, the next two sections of this particular webinar, where I would prompt you to think more than spectra, basically. And the first part we're going to think about when it comes to spectra now is, or the different types of data we can collect, is to think spatially, as in not just basically going to a position on your sample and collecting the spectrum and then moving around and doing that, but actually trying to build into your experiments some interesting spatial experiments as well. So the first part I want to highlight are the two fast mapping modes on the inVia Qontor instrument. And these modes are called stream. So we have two different modes here, StreamHR and Streamline on our instrument. And I think from these diagrams, you probably identify the difference between these two. Basically, StreamHR here is using a point source as our excitation, whereas Streamline is using a line source as our excitation. And what we're doing is we're shifting the sample underneath the laser spot and collecting the data as we go. And with these stream modes, these are faster than the standard map area acquisitions on the instrument because the stage is effectively always in motion when you're operating at the highest speed. So the advantage is you're moving very, very quickly across your sample and the data are streaming towards the detector, meaning that the local energy density is quite low and the potential damage due to heat buildup is also quite low as well, whilst also maintaining a very high rate of data acquisition. The StreamHR mode is the one that will give you the highest spatial resolution. You are getting the sharp laser spot down to a micron or maybe just below as well. So it's giving you your highest possible spatial resolution. It is a point source. We scan the sample underneath the laser spot, and then you basically collect a spectrum at every pixel that you would then process to create your maps. So you're not looking just at a single scattered wave number and generating a map from that. At every single pixel, you are collecting a complete spectrum, and you can process all of those spectra to generate your different maps. In the StreamHR mode, you will have a higher energy density, which will potentially lead to more damage for samples that are sensitive to laser light. And you can use this with LiveTrack to create surface profiles as well. So keeping the laser in focus and keeping your data acquisition of high quality. The Streamline mode, however, will basically stretch that spot out into a line, meaning that you will have decreased spatial resolution. It is, however, it will cover a much larger area more quickly than the StreamHR mode. And the energy density will be lower because you are spreading your laser spot out across a larger area. So there's potentially less damage if you're working with a sensitive material. And because you're spreading that laser spot out across a large area as well, it gives you an opportunity to reduce undersampling when you're doing your mapping. So for example, if you were to have these spots 1 micron apart in StreamHR mode, you are probably undersampling the actual map that you're collecting, because there will be parts that you're effectively missing in your acquisition. However, spreading your laser out into a line means you are now collecting data from quite a few microns in a line, and that line is then scanning across your sample. So you can more appropriately actually sample your areas as well. And again, with Streamline, of course, you can use it with LiveTrack. So you can keep that line in focus on the surface as well. So naturally, this sort of a technique can be very useful for actually mapping inhomogeneous and homogeneous samples as well. But most recently, the work that we've been seeing on our instrument using StreamHR is simply to cover large areas with low intensity, low damage, and get a very good general overview of the composition of samples. So the example I'm showing you today comes from a researcher from WeHi, Elisa, and she has graphene coated TEM grids and has been modifying the surface of these graphene using a UV-Ozone treatment, and is trying to find the optimal amount of oxidation on her graphene to promote the absorption of water during cryo-EM experiments. So rather than simply going to a single position on the TEM grid, capturing a single spectrum and then saying that's representative of the entire sample, what we did was go to multiple positions on the grid and actually collect spectra from a 20 by 20 micron area, thousands of spectra, quite literally, across that whole area, with very short acquisitions, minimizing the amount of damage. And then we can sum all of those spectra together to get that overview composition as well. And so from this, we're able to identify about the optimal UV-Ozone treatment to get the amount of water absorption that she wanted from her TEM grids. And it was somewhere around this 2 to 3 minute UV-Ozone treatment here to maintain the graphene structure whilst also promoting the water absorption onto these particular grids as well. So again, it could be very easy for you to go to a particular spot on your sample, choose a position and look at it and say, that's not what I want, and then assume that your sample is bad. You might go to a few different positions, but it is very easy for you to miss key information when you're not acquiring a huge amount of data over a much larger area with these instruments. So I mentioned LiveTrack already when it comes to these sorts of mapping modes. And basically the way that LiveTrack works is that it works to keep the laser in focus on your sample at all times. And it's not changing the focus of the laser itself, it's changing the Z height of your sample. So if we have, for example, a kind of a rough surface like this, and we are doing an XY raster to capture a map, what LiveTrack will do is keep the laser in focus as you are scanning in X and Y. And it does that by scanning X and Y and then scanning Z as well to keep the laser in focus. So it looks something like this, basically. The laser is, the sample is being moved in X and Y, but to keep the laser in focus on the surface, the stage is also moving in Z and following the topography of your sample. So this can be applied on any of the wavelengths that we have on our instrument and in any of the modes as well. If you are just doing point spectroscopy, you can have LiveTrack active as well, and it will attempt to keep the optical image in focus, or the image in focus as you are moving around on your sample as well. So it can just help to keep things in focus for you while you're navigating. It does work best with samples that don't tremendously scatter the beam, because if the laser is scattered a very large amount, then the camera won't be able to see basically where the good focus is, but otherwise can be applied to any technique. The other method of keeping the sample in focus is a more simple method, but a very robust method as well, and that is called surface, where you effectively define an XYZ plane on your sample beforehand, and then when you define your acquisition and your map, the software will follow that XYZ plane. So here on this particular sample, and this is coming from the Renishaw training module in the software, you can basically go to these different positions on the sample and focus there and tell it to add that XY data point into the software. And then in doing so, you define the outer borders of effectively an XYZ plane. Now, a limitation with the surface mode, of course, is that it effectively only works with samples that are inherently flat, but that are just tilted. So these could be samples that are not quite sitting flat on the actual stage or on a microscope slide, something like this. But what it means is when you have things that are a little bit tilted around the edges where this correction, without this correction, you'll get a drop in intensity like this. With a surface correction, you can then basically get your intensity back across the entire sample. And again, it can help a lot with navigation as well, because if you move around on this plane, it will adjust the Z-axis for you as you are moving in X and Y as well. So this was a little bit of a contrived experiment that I did using LiveTrack recently. After having lunch over at Momo Sushi, I got myself a little fish soy sauce bottle made of polyethylene. It actually says that on the bottle, and we've focused in on one of the scales here of our little fish bottle and used LiveTrack to go across that entire area here. So this is about a 1 millimeter area, and basically capture the white light image across that area. So this is a stitched white light image using LiveTrack to keep it in focus, and then collecting data as well here from the polyethylene. And what you can see, you can actually look at these surface profiles in 3 dimensions and actually see the change, the variation in height here as well with this mode. So you can use this to then define a surface profile on top of which your chemical information can sit. So this is the Raman spectrum focusing on one of these sharp polyethylene peaks here, and then plotted with that Z profile in the background as well. So you can use that to actually enhance your data a little bit and give it a little bit more information and a little bit more context with it than simply a single white light image or no image at all and just a spectrum. Similarly, with the surface profile mapping, this is a embedded and polished cross section. So it's a very flat sample, but when it was sitting on the stage, it just doesn't sit quite level. So we use the surface profile to effectively define a XYZ plane around the area that we wish to map. And then what you can see here is this is a plot of the Z-axis from the stage varying across this area. And you can see that the direction of the tilt is effectively along this axis here. So if we were to collect data from here, for example, compared to here or here, the intensity would be quite different, and we would potentially lose information in these areas where the stage is actually going out of focus or the laser is going out of focus across that whole area. So then the next step up from that is now to actually think about depth. We've spoken about actually using Z to change our heights and basically change where the laser is sitting on a rough surface, but you can also push that laser focal spot into your sample and actually probe to a certain extent the depth information on your sample as well. So what we're doing here is effectively scanning the Z-axis of your sample or the stage, and the laser focus is then pushed beneath the surface of your material, and you're capturing data as you do that scan as well. So in the software, this is called a depth series, and this can give you like effectively a one-dimensional profile of the different peaks from your Raman spectrum. The next step up from that is then to use the stream mode to actually collect a line across the surface. And then after every line segment that you acquire, you change the Z-axis and scan that line through your material as well. And this is now called a StreamHR depth slice in the software. So we define a line in X and Y and then define a depth series as well. So the animation looks something like this. We're basically scanning in X and Y and then changing the Z-axis as well and effectively scanning that line deeper into the sample. Both of these modes are leveraging the confocality of the inVia instrument, which means that they also work best if you're using a high numerical aperture objective. And so on our instrument, that would be the ×100 objective. that has a numerical aperture of 0.85. So your collection volume, your collection efficiency is better, but it's a much tighter focused spot in both X and Y and depth as well. It also benefits from using a shorter wavelength for the same reason. You're constraining your confocal volume a bit more tightly, effectively. It will also work best, of course, on transparent samples. Opaque samples will scatter the light a lot more with depth. So if you're working with, for example, silicon wafers, that is going to scatter very, very quickly below the surface. So your depth profile is going to be basically limited much closer to the surface than it would be for a transparent polymer, for example, or something mounted underneath a glass cover slip. So a few examples here using this technique on our instrument as well. So this comes from Vivek from Quantum Brilliance. And effectively, Vivek is interested in the damage layers from ion implantation in diamonds. So he has a damage layer on the surface, or they're inspecting the quality of these diamonds after annealing and implantation and scanning the laser into the sample through that damage layer. So here you can see a couple of examples of these diamonds, and this is the typical results you would get from one of these depth profile experiments. So we capture, of course, a spectrum at every Z point, and then you are plotting the intensity of this particular peak against the Z value here. So this is the control experiment with the diamond peak plotted as a function of Z. And as we come into focus with the diamond, it rapidly increases and then levels off as we go deeper into the sample. This is then an implanted and annealed sample. So again, plotting the different peaks here, we can see a similar sort of profile going deep into the sample with these particular diamond samples as well. And as I understand it, we actually didn't get through the implantation layer, which told them something basically about their process. This is one of my I've got two kind of contrived experiments coming up now, but this is basically looking at some ink on a polymer here. And so what we've got is an ink layer on top of a plastic, and I'm using the 785 nanometer laser here to then do a depth slice through that particular sample. And the ink and the laminate do have distinct Raman spectra here. And so what we're doing is we're plotting this particular peak from the ink and this peak from the laminate against both X, Y, as in the line scan, and then depth. And so instead of just getting a one-dimensional profile like what we got before with Vivek's work, now what we get is something more akin to a map. But instead, what we're looking at here is a slice through the sample. So it is inverted in this particular case, just because of the way that I set up the experiment. But 0 here is nearest to the surface. And you can see the intensity of this particular peak from our ink is almost entirely at the surface. And then below the surface, we have the intensity from our laminate polymer that then decays with some amount of depth as well, as it then gets in towards the paper in the laminate as well. So we can see that this particular signal is at the surface of this particular sample. And you can do this with multi-layered samples, for example. So this is another little test experiment where I have two different polymers, but stacked with 3 layers. So I have 2 layers of PET sandwiching a layer of polypropylene in the middle, and they're both about 4 microns each, stacked as a laminate, and we're doing a depth slice through here. And these are our different spectra. So we have the PET and the polypropylene, and this is then the sum data from the slice. And we can plot these particular distinct peaks here and see how they vary with depth. So our PET signals are most intense at the surface and then deep subsurface. But then this is our polypropylene signal here that is sitting in between our 2 PET signals. So this is an example basically of a multi-layer polymer laminate, and we can show the depth of those different layers as well. Okay, so that was thinking spatially. Now let's think a bit differently, and let's think thermally about what we can do more with our instrument. So here we're talking now about the heating and cooling capability on our inVia using the Lincoln stage that you see here. So this is a Lincoln THMS 600, and basically it gives us heating up to about 600 degrees Celsius and cooling down to about 120 Kelvin, or about minus 150 degrees Celsius. It is limited to using the ×50 objective because that's the long working distance objective, and you need that to be able to actually focus down inside of the instrument. Using it is relatively straightforward for your sample preparation once you know how to cable the instrument, but effectively you will place this little egg ring holder onto the heater, then you place a cover slip onto the heater to protect the heater, and then onto the cover slip you place your sample. And beyond that, there's not a lot else to it. You then focus on your sample, and everything else about the Raman spectroscopy is basically the same as well. So some examples from our users. So this is Melinda's work from Monash MIPS, the Institute of Pharmaceutical Sciences. And she had some sandwiched emulsions between two cover slips sitting directly on the heater, and the heater was set at 37 degrees Celsius. So basically using these at a physiological temperature to look at lipids and phospholipids and triglycerides in particular with her work. This is very early work, but effectively what she's looking at in particular here is this band up around the 2900 wave numbers, which tells her information about things that are in the crystalline and the liquid state in particular. So holding the samples at 37 degrees and then changing things about her particular sample and looking at different parts of the sample as well, she can spot different bits of information about the crystalline and the liquid state of her emulsions in this particular work. From chemical engineering here from Taha and Peter, we have a dropped cast film of a material on a cover slip and ramping the heater here from room temperature up to 80 degrees Celsius allows us to see a phase change in that particular material. So what you see here is, this is a 2D representation of all of the Raman spectra here against time. This is the temperature ramp against time as well. So you can see going from room temperature up to 80 degrees Celsius and then back down to room temperature again. And the spectra you can see go from having some Raman active components here to being Raman inactive at 80 degrees. So a phase change has happened from here to here, and then back down to room temperature. That phase is then recovered again once you get back down to room temperature. So this is investigating the phase information of different materials as well. And you can use also the cell to do chemistry. You can look at in situ studies and chemical reactions. So again, from chemical engineering with Jingxi, Ali, and Kevin Lee's group, what we are using the cell here for is to flow nitrogen gas through this to keep an inert atmosphere inside of the chamber, while the chamber or the heater is then ramped from room temperature up to 200 degrees Celsius with lithium gallium droplets sitting on top of a cover slip here. And then the laser is focused onto the droplet, and we're looking for the spectra that, of particular chemistries at the surface of this droplet. And what they found was once they hit the 200 degrees mark, they were actually able to form this lithium nitride material right at the surface of their lithium gallium alloy. And so this only happens under an inert atmosphere at 200 degrees. If this was to happen in an oxidizing atmosphere, so as in without the nitrogen flows, a dry atmosphere, then they just get oxide peaks instead of the nitride peaks as well. So here we're doing some surface chemical reactions inside of the cell as well. Okay, that's everything that I wanted to go through. And what I'm hoping that you might be getting out of this, and what I really want you to get out of this, is to basically think beyond just spectra with this particular instrument, and try to think of new and interesting ways you can leverage the capability of this instrument to evolve your work a little bit more and not just use it as a simple workhorse Raman spectrometer. So that's everything that I wanted to go through, and I now welcome anyone to ask any questions. And you can go ahead and unmute yourself, pop questions in the chat. This is really a Q&A discussion time now. So thank you very much for coming and for listening.